Imagine a cosmic web, a large-scale structure of the universe that has taken billions of years to form. In the dawn of time, there were no stars, galaxies, or larger structures. The universe was a smooth canvas with areas of slightly denser and less dense than average. Now picture tiny imperfections, or density fluctuations, scattered across this uniform canvas. With the pull of gravity, these fluctuations began to draw material towards them, leading to the formation of stars, galaxies, and other cosmic titans over eons. A fascinating process, isn't it? But it's not all. This cosmic web is a hierarchy, forming smaller structures first, then gradually larger ones. From stars igniting within the first 100 million years of the universe's existence to the appearance of galaxy clusters billions of years later. But there's something more. Something that... you'll know shortly. Hey there, curiosity explorers. Ready for another dive into the unknown? I'm your host, Cesar, and with me is the perspicacious Sonia, ready to help us unravel mysteries of the cosmos.
Hello, cosmos enthusiasts. Don't forget to strap in for another exciting journey into the depths of space and time.
And remember, your interactions fuel our journey. Don't forget to subscribe to the Curiosity Wonderland, leave us a comment, and share our adventures with your friends. Together, we can explore the cosmos one curiosity at a time. Picture this, the universe, teeming with hundreds of billions of galaxies, each home to hundreds of billions of stars, surrounded by trillions of even smaller galaxies. Quite mind-boggling, isn't it? Now cast your thoughts back to a time closer to the Big Bang, a time devoid of stars, galaxies, or any larger-scale structures. Instead, all was smooth and uniform, with little to no clustering. Think about the densest regions being a mere thousandth of a percent denser than average, and the least dense regions being just a few thousandths of a percent less dense than the cosmic average. The universe, you see, was born with only very tiny imperfections, but gravity, that relentless force, caused those density imperfections to grow as the universe expanded. Depending on the rate and location of this growth, we now have a cosmic tapestry of galaxies and galaxy clusters interspersed with near-empty cosmic voids. The cosmic structure we see today didn't form all at once. It was a gradual process, with the largest structures being the last to form. Imagine, if you will, the universe in its early stages, filled with both normal and dark matter, and radiation evenly distributed almost everywhere. Isn't it astounding to ponder how the universe has evolved from this early state of uniformity to the clustered spectacle we see today? It's like watching an artist paint, starting from a blank canvas, adding tiny strokes of color, which over time transform into a stunning, complex masterpiece. Imagine these minuscule deviations in the early universe serving as the seeds to the grand cosmic structures we see today. Now let's pause to reflect. Isn't it incredible to think of our place in this cosmic web? How the blip of our existence is woven into this grand tapestry of the cosmos. I'd love to hear your thoughts. Enjoying the journey so far? Don't forget to engage with us. Let's continue to unravel the mysteries of the universe, one curiosity at a time. Here's an intriguing tidbit. The density fluctuations in the early universe were almost the same on all scales, from kilometers, light years, to even millions or billions of light years. All these regions had the same ratio of a 1 part in 30,000 fluctuation from the mean.
So basically, despite the vast differences in scale, the universe was pretty much uniform in its density fluctuations.
Yes, that's correct. The regions that were slightly denser than average at the universe's birth evolved over time, but their growth was limited by several factors. 1. The initial small magnitudes of the overdensities. 2. The cosmic scale on which the overdensities are found, which plays a role in how long gravitational force takes to traverse them, and the presence of still energetic radiation.
Could you expand more on the concept of energetic radiation?
Well, the presence of energetic radiation, especially in the early universe, essentially puts a limit on how fast structures can form. It takes anywhere from tens to hundreds of millions of years to form the first stars, although small-scale clumps of matter exist long before that.
Fascinating. So did the stars, galaxies, and galaxy clusters all suddenly appear?
Not quite. The universe's structure formation is hierarchical. The smallest scale structures like stars and star clusters formed first. Galaxies, galaxy groups and clusters, and even larger cosmic structures came into existence much later. In fact, it took under 100 million years for the first stars to form, but billions of years, more than 10 times as long, before the formation of the massive galaxy clusters we see today.
So the cosmic microwave background we observe today is a remnant of these early density fluctuations.
Indeed. The fluctuations seen in the cosmic microwave background are consistent with the idea that they originate from a scale-invariant set of quantum fluctuations. Interestingly, their magnitude is so low that they could not have arisen from an arbitrarily hot, dense state. Now, this might appear counterintuitive because the seeds of structure exist on all scales from the get-go, and the laws and rules of gravity are ever present. Anything with mass or energy, in any form, experiences gravitation. However, a fundamental reason for the existence of hierarchical structure formation is evident even in the earliest image we have from the infant universe, the cosmic microwave background and the fluctuations inherent to it. Here's an important clarification: even though gravity is an infinite-range force, it doesn't propagate at infinite speeds. It moves only at the speed of light. So, if you are to affect a region of space that takes 100 million years to reach at the speed of light, it cannot feel your presence until 100 million years of time have passed. This is the reason why in the graph of the spectrum of fluctuations within the cosmic microwave background, the largest scales have temperature fluctuations that are completely flat. Gravitation hasn't impacted them yet. The 380,000 years that have passed from the time the hot Big Bang first occurred until the cosmic microwave background gets emitted, even within the expanding universe, hasn't provided enough time for those large cosmic scales to experience the influence of gravity. The first significant peak in the graph is where gravitational contraction is just taking place now, but there hasn't been enough collapse to trigger pushback from radiation. And the peaks and valleys beyond that represent a splashing around on scales smaller than the current cosmic horizon. This is where gravitational contraction has not only occurred, but where radiation has pushed that once contracted matter back out again at least once. This understanding leads to a detailed roadmap for how the large-scale structure in the universe forms. The smallest scales collapse first, while larger scales require longer cosmic times to become overdense enough to form structure. Note that filaments and rich clusters, which form at the intersection of filaments, arise primarily due to dark matter. Normal matter plays only a minor role. It's like watching a cosmic dance unfolding over billions of years, and we're just beginning to understand the intricate steps. So, if we break it down into general rules, we find that structure forms on smaller scales first. Stars come to be before galaxies, galaxies before clusters, and clusters before superclusters. The particular scale where the density fluctuations have the greatest magnitude will correspond to a distance scale in the present day, where we are more likely to see galaxy correlations than on either shorter or longer scales. If there's some sort of acceleration phase that arises later in the universe, like dark energy, it will cause a cutoff in structure formation, indicating a maximum, largest scale for any structures that can stably exist. And once you become gravitationally bound, you should remain gravitationally bound even as the expansion of the universe continues without bound. These predictions have been borne out spectacularly based on our observations of both the nearby and the distant universe. The first stars, as we understand them, appear when the universe is between 50 and 100 million years old. Star formation at this stage requires many millions of solar masses to gather together in one region of space, initiating gravitational collapse, for some of that material to fragment and lead to the formation of individual stars. This is an exceptionally large amount of material, which is special for the primordial material that the universe was born with. This means that even the densest regions of all won't develop stars until many tens of millions of years have passed. Then it will take additional time for these individual star clusters to merge together and to accrete matter from the surrounding regions, in order to create the first galaxies. After these galaxies come into existence, it will take several hundreds of millions of years for significant numbers of those galaxies to merge together to create evolved galaxies and galaxy groups, and for those groups to merge together to form galaxy clusters. This is the hierarchical formation we talk about when discussing the cosmic web and the large-scale structure of the universe. It has to build itself up, from small scales to large ones. The grand scale of this phenomenon is truly awe-inspiring. There is a protocluster of galaxies known as A2744Z7P90D, found just 650 million years after the Big Bang. These galaxies are not yet gravitationally bound together, but with time, they will be, and end up forming a galaxy cluster upwards of 1 quadrillion solar masses. This structure's formation in the universe eventually leads to a network of filaments that intersect at various nexuses. However, this network doesn't just appear everywhere at once, it starts on smaller scales first. The larger scales don't exhibit structure, or rather, the growth of structure beyond the magnitude of its initial seeds, until the universe has aged further. It takes an incredibly long time for a gravitational signal to traverse the large distances separating the clumps of matter that form structure on the largest scales of all, spreading hundreds of millions, or even billions, of light-years apart. By the present time, our observable universe is about 92 billion light-years in diameter. Given how large the universe was at an age of 380,000 years, and the size or scale of the acoustic peak we saw in the cosmic microwave background, it sets the scale at which we're more likely to see galaxy-galaxy correlations.
And that's where the fascinating part comes in. That acoustic scale today is at a distance of about 500 million light-years. So if you put your finger down on any galaxy and look a certain distance away, you're more likely to find another galaxy 500 million light-years away than you are either 400 or 600 million light-years away. It's like the universe has its own peculiar rhythm and pattern.
Exactly. It also explains the first cosmic bounce we've ever discovered, a bubble-like, galaxy-rich structure spanning approximately 500 million light-years in radius. But it's important to note that the large-scale features we recognize as galaxy clusters aren't present at the earliest stages of cosmic history. For many hundreds of millions of years, there should be no galaxy clusters at all, only protoclusters still in the process of forming, at best. If we want to see large groups of galaxies all clustered together in the same region of space, and all gravitationally bound together on top of that, it should take billions of years of cosmic evolution before they appear. Large collections of galaxies will inevitably clump and cluster together, as gravitation on those larger cosmic scales will eventually catch up, drawing them in towards their collective center of mass. It takes time for these larger, more massive, grander scale structures to form. In the universe, we have all the time we could possibly need. The galaxy clusters that appear at these early times should be lower in mass than the ones that show up at later times, as even on these large scales, there's still ongoing gravitational growth over time.
You know, this reminds me of a childhood memory. When I was young, I remember my dad explaining to me how mountains were formed. He would take a handful of sand and pile it up slowly, demonstrating to me that it took a lot of time and pressure to create something grand. The concept of galaxies forming and evolving over billions of years feels very much like that slow and patient process.
That's a lovely analogy. Just like your pile of sand, the earliest massive galaxy clusters we know appear well after massive galaxies are plentiful. The farther away we look, the lower in mass galaxy clusters are, while the earliest protocluster we find has only a few handfuls of galaxies inside it, and still requires nearly 1 billion years to begin taking shape. Most spectacular of all, there seems to be a limit to the size and mass of structures. We have our local supercluster, Laniakea, which contains the Milky Way, the Local Group, the Virgo Cluster, and many other clusters and groups that appear to be arranged in a web-like structure. But Laniakea itself turns out to be more of a phantom. It's important to understand that Laniakea, despite its awe-inspiring scale, is not a true structure.
You mean it's not bound by gravity, like other structures we've been talking about?
Exactly. On the largest cosmic scales, dark energy dominates the gravitational force. This has been the case for the past 6 billion years.
So bigger isn't always better in the universe?
In a sense, yes. If an object hadn't gravitationally grown to a sufficiently high density so that it would collapse under its own power by a specific point in cosmic history, it will never reach that point.
And I presume Laniakea is one such object.
Correct. Large supercluster scale structures like Laniakea are currently being torn apart by the expansion of the universe.
That's mind-boggling. How long does it take for these large galaxy clusters to form?
On average, about 2 to 3 billion years. But despite the deceptive looks of the image, even Laniakea isn't a real structure, as dark energy will continue to drive most of these clumps apart over time.
So are there no larger structures than galaxy clusters in the universe?
The accelerated expansion of the universe is simply too much for gravitation to overcome. So no, there are no bound structures larger than galaxy clusters within the universe.
It seems like the universe has its own limits, after all.
Indeed it does, and that's part of the beauty and complexity of the cosmos. The cosmic web, this grand tapestry of galaxies and galaxy clusters that we've been discussing, isn't growing as it once was.
So dark energy is causing it to stretch instead.
That's right. The filaments within the cosmic web stretch and stretch due to the presence of dark energy. So in a way, we're at a unique point in cosmic history.
That's kind of sad in a way.
Perhaps, but it's also a reminder to appreciate what we have while we still have it. The observable universe will never be as richly structured as it is now. It's truly a spectacle worth savoring. So in this cosmic voyage, we've unraveled the mystery of how the magnificent cosmic web, the large-scale structure of our universe, came into being. Starting from essentially uniform beginnings, the universe slowly sculpted itself into a grand masterpiece, with the tiniest imperfections acting as the initial brushstrokes.
It's an awe-inspiring journey, spanning billions of years and culminating in a spectacular cosmic tapestry. And who knew that the largest structures we see aren't even gravitationally bound? It's another testament to the wonders of the cosmos.
We've peered into the past, traversed through time, and come back with a deeper understanding of our place in the cosmos. It's like we're part of a grand cosmic puzzle, and each discovery brings us closer to seeing the full picture.
That's beautifully put. We'd like to thank you all for joining us on this incredible journey. If you enjoyed this episode and learned something new, remember to hit that like button.
And don't forget to comment your thoughts and share this episode with your friends. Let's keep exploring the cosmos together.
Until next time, stay curious and keep looking up. Goodbye, everyone.
Goodbye, and keep wondering. Our cosmic journey was inspired by the article, "What Was It Like When the Cosmic Web Formed?" by Ethan Siegel on the Big Think site, published on January 24th, 2024. If you want to immerse yourself more in the topic, the full URL is in the description. Until next time, folks.